Hi, welcome back. We're covering aircraft instrument systems. Today we're looking at the pitot systems, mostly the airspeed indicators as part of this, but we'll see this way how they actually operate. Basically, we're talking about the primary flight instruments that are connected to the pitot tubes or system. Static is not a tube. It's just basically a calibrated orifice, a hole in the side of the aircraft. And the pitot tube is a pitot tube, which usually points into the airstream. Of course, the static line does not. It's off to the side where it's between the two. They can measure the difference of pressure, which can be interpreted into these three instruments. Some of the more important flight instruments derive their indications from measuring air pressure. Gathering and distributing various air pressures for flight instrumentation is the function of the pitot system. On simple aircraft, this may consist of a pitot system head or pitot tube with impact and static air pressure ports and leak-free tubing connecting these air pressure pickup points to the instruments that require the air for their indications. So these pitot line, the blue line would be the leak-free tubing, so they can carry the pressure directly to the instrument. The altimeter, airspeed indicator, and vertical speed indicator are the three most common pitot instruments. And in this presentation, we're going to mostly talk about the top two, the airspeed indicator and the vertical speed indicator. The altimeter, we'll save that for its own presentation. And right offhand, you can see that the airspeed indicator on top is actually connected to just the pitot tube. Indirectly, it's connected to the static port. Excuse me. And the vertical speed indicator is basically attached to the other instruments, so it's actually receiving the pressure from the pitot line, and it's got a direct, what appears to be a direct line right to the static port. All right. I see we're off the screen a little bit, so I think I'm just gonna drop off the screen here. All right. Still wearing my glare glasses, mostly for the lights that I have around me. Here's some detail. A pitot tube is open and faces into the airstream to receive the full force of the impact air pressure as the aircraft moves forward. So then we call that ram air. The arrow is indicating the ram air entering the tube. This air passes through a baffled plate, which you can see illustrated, a little black donut type around the tube. It's designed to protect the system from moisture and dirt entering the tube. Below the baffle, a drain hole is provided, allowing moisture to escape. There's a static hole. Where's the little drain hole? It's way here in the back. Especially with the ram air coming in, any moisture is going to be driven into this little corner. So that's where they place the drain hole. The ram air is directed aft to a chamber in the shark fin of the assembly. An upright tube or riser leads this pressurized air out of the pitot assembly to the airspeed indicator. And the red would be the riser tube, taking it directly to the airspeed indicator, which shares the information with the other two, the vertical speed indicator, VSI, and the altimeter. Some pictures of it. It's mounted on the outside of the aircraft where it can pick up airflow that passes the aircraft. As the speed of the air increases, the pressure inside the closed pitot system also increases. So you can imagine the air pressure is, think of it being compacted. The faster the aircraft is going through the atmosphere. So the air pressure increases. And you can imagine if the aircraft slows down, the pressure in the pitot tube also decreases. And you can take those measurements and calibrate them onto various instruments, including the airspeed indicator. Here's some pictures of the static port. They're typically mounted flush on the exterior of the aircraft. The sensing holes are aerodynamically critical and should not be cleaned with a tool. So they're talking about their first little maintenance here. Yeah, what if you see that they're clogged? Do you use a tool? You can see that, count the number of holes and see how many appear to be open. And if they're not, what would you use? Not a tool? A toothpick? Just know that you cannot clean them with a tool. Then there's going to be maintenance also in the pitot tubes. As, the little bugs like getting in there to make their nests, little mud flies. Usually you clean them with air, compressed air, if you're able to without disrupting the instruments, which you wouldn't want to blow it right in here because they're connected by tubes to your instruments. There's usually multiple systems in most transport category aircraft. You can see there's a captain, a first officer, and even auxiliary. 3 different colors of tubes that are in effect going to 3 different pitot tubes. 3 different the X's would probably be the static ports, I believe. Let's see. I don't see them otherwise. I guess they're just they're not really illustrated. They're just at the ends of the tubes here. 3 different airspeed indicators. Well, just 2 in this picture. And then 2 VSIs, and actually 2 Mach, which is a fancy airspeed indicator, a Mach meter, and 2 altimeters for altitude. And rate of climb is what they're calling the VSI, the vertical speed indicator, which is how fast are you going up or down. So rate of climb probably makes a little more sense. Because when you think of the speed of the aircraft, you're mostly thinking about its horizontal speed, not necessarily its speed vertically. There's a heater in the pitot tube because that moisture may freeze because of the the environment that the plane is flying in. And you can see that there's some, here's a 100-watt heater here and a 35-watt heater here. So the 100-watt heater would probably even heat the front because it's enough heat being generated. And the 35 is to make sure that the water stays liquid enough to escape through the drain hole. Of course, with the heater, you're going to have a power source, and there's a little contact, a double contact, which will connect to the power source. There's safety concerns about grabbing hold of a pitot tube because the pitot heat might be on. And there's been stories of people who really burn their palm quite badly. Apparently there's a slide here that shows that there's combination pitot-static. In this illustration, apparently the pitot tube is in the front of this little fin here, and the static port is on the bottom. I wouldn't be that much concerned about that. I'm kind of curious as to where they would put the drain hole if the pitot static port is in the bottom, but they're not common enough to actually explore into a little cross section. If you have a plane like that, look into it further. The static routing. Static pressure is provided for the airspeed indicator, altimeter, and vertical speed indicator, so all three. Some aircraft may also have a static pressure routed to a cabin altimeter, standby altimeter, or a separate altitude encoder. I think I noticed that briefly on the multiple system slide that we looked at earlier. There was they also had a cabin altimeter attached to it, which would in effect it's well, we're not going to worry about that too much right now. A cabin altimeter, we'll cover that a little bit more in cabin environmental or cabin atmosphere, however you refer to the class. An alternate static line, air valve. An alternate air valve is located where the pilot can select an alternate static air source if the primary source becomes plugged. Okay, this is the mechanism inside the flight deck or the cockpit. Usually over on the co-pilot side, on the side wall, where you can actually change if your instruments are acting up, especially your altimeter, which seems to be what they mostly are concerned with. You can switch over to an alternate static source and I would suppose the simplest way to explain it would be if you push it in, apparently that's going to connect this tube with the alternate. If it's pulled out, it's connected with the static port, the normal static port, the unobstructed static port. All right, let's take a look at some of the questions. Which instruments are connected to an aircraft's pitot-static system? And they're giving you 5 options. And I don't really like one of those last slides because it started to talk about the cabin altimeter, which is also on the list. So, and there's also a cabin rate of change indicator. I'm not thinking that's what they're looking for. Matter of fact, those we're going to cover that in another class, but I'm going to go with the other 3, 1, 3, and 5, which looks like it'd be answer C. I suppose there's an argument to be made that it's all 5. That's why some of these older FAA questions are a little trickier, so just be aware of them. I mean, my answer is going to be C, but I could be wrong. Let's go ahead and take a look. It is C. It's the primary. They should say which primary instruments. Um, an oral question, which is, you're not going to have much problem with the oral questions, because if there is a distinguishing factor, you can explain it since you're actually verbally answering the question. Your DME might ask, what aircraft instruments are connected to the pitot system? Well, at this point, I think it's definitely fresh in your mind. The airspeed indicator, the VSI, vertical speed indicator, which could also be referred to as rate of climb, and the altimeter. Let's see what they answer. They're also talking about the Mach meter in high performance jets. I would imagine you get to you're getting up to the speed of sound, which is what Mach 1 is. I would imagine that the air pressure inside a pitot tube is different. So you would need a more specialized instrument. Okay, a very similar question. Which instruments are connected to an aircraft's static pressure system only? Okay, we would have had to been looking at the charts there. What are the options? A is the VSI and the altimeter. B is the cabin altimeter. Okay, I'm going to drop that one right away. As a matter of fact, because number 4, the cabin rate of change indicator, is in both B and C, I think from the process of elimination, I'm going to say 1 and 3. But it's, however you get to the correct answer is fine. That does seem to be a good strategy there. So basically, this type of question, look for the ones that you can eliminate. In this case, you eliminate all but the right answer. All right, since we're talking about this, the cabin altimeter and the cabin rate of change indicators sense their static pressure from inside the cabin. Okay, so, and I guess they would not refer to that as a static port, so it's not really connected to the pitot system, since it's reading the inside cabin or flight deck pressure. So that would be the distinguishing. Yeah. Okay, third question. What will be the result if the instrument static pressure line becomes disconnected inside of a pressurized cabin during cruising flight? Well, it's a good thing we took a look at that, because we were talking about reading the pressure in the cabin. It's not really a pitot port. A static port. So this is kind of the same thing. Instead of reading from the static port, it's going to read from inside the cabin. So what does it say? The altimeter and airspeed indicator will both read low, or B, they'll both read high, or C, the altimeter will read low and the airspeed indicator will read high. Now, I think if you can come up with the altimeter, you should be fine on that. Let's say, so instead of reading the low pressure at altitude, if it's actually reading from the outside atmospheric pressure of aircraft, say at 10,000 feet, it's going to read low, maybe less than 10 psi. But in the cabin, you're going to keep it up higher. So the aircraft is going to think that it's actually closer to the ground. So the altimeter is going to actually read low. So which one does that say? So that could be A or C. Okay. How about the airspeed indicator then? Would that read low or high? Um, well, its airspeed indicator is measuring the differential between what's in the pressure that's building up in the static in the pitot tube and the pressure that's on the side of the aircraft. So uh, there's not going to be as high a differential if the cabin is, which is a higher pressure than actual, uh, and the is going to read high, so the differential is going to be smaller between the two. So I would say it's also going to read low. Long-winded way to get to the correct answer, A. So both the altimeter and the airspeed indicator will read low. Now the altimeter is a little easier to come up with. The airspeed indicator, you have to basically visualize the differential, which would be there would be a smaller differential between the pitot and what the static tube is now reading. Oral question: why should you avoid cleaning obstructions from the sensing holes in a pitot-static system with a tool? Why couldn't you just stick your what's your little pointy instrument there? An owl, AWL, or a toothpick, I guess. Well, for one thing, it'd be hard to do. I mean, you'd in effect just be pushing the debris deeper into the port. You wouldn't, in order to scrape it out, you might actually disrupt you might increase the size of the hole inadvertently, and the holes, the sensing holes, are aerodynamically critical, so you don't want to mess with them. Aerodynamically critical, okay. Well, I have had the course a few times, so. Took it once and taught it 5 semesters. All right, getting to the airspeed indicator. No, we did look at that in other areas. The dial on this airspeed indicator can be rotated similar to the scale on a circular flight computer. Okay. When the air temperature is lined up with the pressure altitude, the true airspeed can be read from the outside scale. This is more of a pilot's issue, but they basically can rotate the outer edge so that you can actually read the numbers, the outside numbers, which will also show you not only what it'll actually show you what the airspeed is based on the actual temperature. Air temperature, yeah. I guess that's what it is. Okay, there's the temperature up on the top. So you're adjusting for temperature, which will actually give you the pressure altitude. I believe there's a few questions. It's mostly pilot questions, but let's see what the technicians have to answer. There's true airspeed indicator, I guess, TAS. It contains altitude and air temperature correction devices in order to indicate true airspeed. All right, so what is the TAS? It's the equivalent airspeed corrected for non-standard pressure and temperature. The speed of sound decreases as altitude increases due to the lower air temperature. All right, so I imagine that might be a little contrary to what you would maybe think. It's like, well, there's less friction in the air. If there's less air, wouldn't sound waves travel faster? Well, apparently not, because of the high temperatures at altitude. So what does this scale say? That at ground level, the density ratio, we got a pressure ratio, the temperature is at 59, which is standard, and that's the speed of sound in knots. So if we go up to 10,000, we can see that there's a 73% density ratio, much lower than 1 for pressure ratio. Temperature at 23 degrees. Let's see how that affects the speed of sound. Yes, it did. It slowed down to 600, from 661 to 638 knots. You'll notice it actually gets down to a point at 30,000 where it just stays the same, and then it actually increases. So if you're thinking of space, I guess, does it increase? Slightly increases. It doesn't go back to the 661. A Mach meter, we mentioned that briefly. It is an airspeed indicator that's adjusted for altitude in order to indicate airspeed in relation to the speed of sound. So it's more like a percentage, or the equivalent. 1.0 is the speed of sound, and Mach 2, which isn't even on this scale, but Mach 1.4 would put you over in this range. And if you're at about Mach 0.5, you're at half the speed of sound. This one indicates that the airplane is flying at 83% of the speed of sound. Is there anything special in the diagram? We can see our gears and our coil. You can see mechanical connections. I don't see the pitot or static. I do see an airspeed calibrating mechanism. And this could be a pitot or static, or both. Or maybe they're just, I'll have to look in that a little bit more. Here's a combination airspeed indicator, which allows airspeed, Mach, and maximum allowable airspeed. The airspeed indicator shown here is used in early models of the Boeing 747 and combines airspeed and Mach indications with a barber pole pointer to show the maximum allowable airspeed. The instrument also displays calibrated airspeed on the lower digital counter. 5 white bugs can be manually positioned by the pilot to provide visual reminders of critical flight speeds for various flight regimens or regimes, such as takeoff or landing. True or false question. An airspeed indicator measures the differential between pitot and static air pressures surrounding the aircraft at any moment of flight. Ties into the last question we answered. Yes, that's the differential. That's why when the line came loose inside the cabin, that the differential was not as great. So true. Usually these come in pairs. Same one. Actually, when you see the test, it'll give you some options. Only the first one's true, the second one's true, or they're both true, or they're both false, or something like that. So it kind of makes up for a 50-50 chance on guessing a multiple choice question, true or false. So you pretty much have to know them both in order to get to be satisfied that you're going to have the correct answer. What's the second one? An airspeed indicator measures the differential between pitot and cabin air pressures at any moment of flight. So no, that one is not because of the cabin. I think you could start to see a trend here in the type of questions that they're asking. And of course, it is not true. It does not measure the difference between pitot and cabin air, but it measures the difference between pitot and static air, or outside static air pressure. So if they ask you which one, yes, only number one would have been true. Now we've talked about the vertical speed indicator a little bit, also called rate of climb. It indicates the result of the change of the static pressure. So I guess it doesn't really, because you're not that concerned with your forward speed, it doesn't really factor into the pitot tube. So it's just reading directly from the static port, kind of like an altimeter. Okay, we're going from pressure factor of 20, all of a sudden we're down to 15. If that happens over a minute, you're going to get a certain calibration. And it looks like they're using bellows or two diaphragms on the inside. There's a calibrated lake. I suppose that's one of the trivia things about the VSI is the calibrated leak. Again, that's an aerodynamically type critical, or actually they don't use the words when it's inside the instrument like that. It's just a precisely sized hole which allows some leakage, which also allows the differential from the cabin, I guess. So let me back up on that. Otherwise, it's the same type of leakage. What do we call that? A carrier gear and a keep wanting to call it pinion, but apparently it's not. What was it? A spur. We have our little coil in here. Basically, the mechanism, the mechanical portion is what we're used to seeing, except for the calibrated leak. That's why I call it a little bit of a trivia. And since it's a leak, it must be the excess air pressure is relieved out the side. Which makes sense, because otherwise it would just say that you're continuing to climb, but once you level off, then the bellows would have an opportunity to contract as the excess pressure is relieved through the calibrated leak. All right, I guess I never looked at it that closely. Instantaneous VSI. So rather than being operated on bellows, they use something else. Sure does look like they have bellows in there. It looks like they're compensated with devices known as accelerometers, actuated pumps or dash pots. There's an inlet from the static port, same issue, and there is a calibrated leak, and the rest of the mechanism looks the same as what we've already looked at. Apparently that can give you instantaneous results on your instrument. The pointer, as the differential pressure changes, the diaphragm expands or contracts, causing the pointer to indicate changes in airspeed. I think we already looked at that. Anything else? Bellows, Pitot tube. Pinions. See, they're calling it a pinion gear, so I don't think I was that far off. Sector gear. I like that better. Hairspring. All right, I'll start referring to that as a hairspring. Shaft, lever. I think we're pretty much used to those terms. An accelerometer. Showing G force, G units. That's usually the force that is that like test pilots would experience when they're doing extreme maneuvers. How much force is being pushed by gravity, centrifugal force. That can be also measured by a device, an indicator known as an accelerometer. In some aircraft, certainly, I would imagine military would have more of this. That indicates the present G forces acting on the aircraft plus the maximum negative and positive G's experienced since the accelerometer was last reset. Yeah, you certainly don't want to exceed the structural limits of the aircraft, so that type of reading would be handy. Tachometer, we're pretty much used to these in our vehicles. As a matter of fact, isn't this one from a vehicle? That doesn't really look at like the typical Hobbs meter. No, it's a Jepson slide, so. Which, as you can see, I'm leaving the copyright material, even though this is educational. We can see, the green radial line. We can also see a red radial line, and a red arc and a red radial line and the green arc. And what appears to be an odometer, but it is an hour. Okay, so certainly your automobile isn't going to measure by hours into the tenths and 100th of an hour. What operating parameter is indicated by a tachometer? What does that tachometer read? Since we're mechanics, we pretty much know that a tachometer is going to read the engine speed, specifically what part of the engine. Well, you can't really say the reciprocating engines. You can't really say the pistons indirectly. What is actually measured is the revolutions per minute of the crankshaft. And then I suppose the thorough answer would then be to also answer for turbine engines. And since it does not really have a crankshaft, there is kind of a connecting shaft between the various fans. Let's say it would probably be it would probably be the compressor vanes. Let's see what they say. Engine RPM, crankshaft or turbine rotor speed. All right. Probably didn't answer that second one correctly. Turbine, one of the turbines, if you could. Yeah, that's a good answer. So the crankshaft, we knew that because that's general knowledge from vehicle operation of reciprocating engines. Turbine engines is new and more certainly used in aircraft predominantly, and so that'd be turbine rotor speed. All right, it looks like that wraps it up. All right, thanks for joining, and we'll see you on the next one. Bye.